Most creek walkers step over them without a second glance. Tiny grains of black sand, dull red slivers, or oddly greasy-looking pebbles hiding just beneath the surface. These overlooked particles are often the very trailheads of buried diamond paths, quietly marking locations where centuries of erosion have released clues from upstream pipes and ancient alluvial beds. The real misfortune isn't the stone itself. It's the failure to recognize what builds around it. Beneath almost any river or creek that cuts through ancient, stable geologic terrain, there lies the potential for something extraordinary. Yet, raw diamonds do not announce themselves with brilliance. They lack the flash that draws attention in cut form. Instead, their value hides behind a matte to oily luster, irregular but often octahedral shapes, and a peculiar resistance to scratching. While casual collectors pass by glittering quartz or mica flakes, those trained to notice the subtle traits of diamond indicators see a completely different map in the sediment. The first lesson is not to search for diamonds directly, but for what travels with them. In places where volcanic pipes once delivered diamonds from the mantle, kimberlite or lamproite zones, fragments of pyrope garnet, ilmenite, and chromite often accompany the erosion tailings. These heavy minerals, denser than quartz or feldspar, accumulate in black sand layers behind boulders or inside river bends where the water slows. A quick sweep with a magnet may tease out ilmenite or magnetite grains, an encouraging sign if you're near the right geology. In old placer zones, especially in river systems downstream from cratonic shields, such as parts of Canada, Brazil, or southern Africa, diamonds settle like gold in natural riffles, wedging themselves between heavier gravels. But unlike gold, you can't rely on color. Instead, you need to recognize habit. Small crystals with rounded edges, sometimes with trigons or pitting on the surface from natural etching. Even a single such stone, if found with corroborating indicators, can shift the entire valuation of a location. Many first-time searchers miss the importance of sediment contact points, where old gravel meets bedrock, or where flood layers stack across centuries. Diamonds, like other heavy minerals, settle low. That means checking not just surface gravels, but the deepest accessible layers in a creek cut or dry bank exposure. It's tedious, but skipping this step leaves most of the real clues buried and unread. As prospectors once said, "The gold is in the details." For diamonds, the saying holds, except it's the garnet that gives the first word, the ilmenite that adds urgency, and the stone itself that may rest just inches deeper, waiting to be seen by someone who knows how to look. But even if you're in a promising location, how can you actually tell a rough diamond from the quartz and glass fragments that seem so similar? Most raw diamonds don't sparkle. That's what throws off even experienced collectors. In the wild, a diamond isn't the fire-flashing centerpiece you see in jewelry cases. It's a pale, greasy-looking crystal that blends into the wash of gravel unless you know exactly what to look for. The at-a-glance difference between ordinary creek pebbles and a candidate rough diamond begins with three subtle cues: luster, form, and translucency. But misreading any of them can lead to frustrating wild goose chases or worse, tossing a true find back into the water. Start with luster. Unlike quartz, which flashes with a vitreous glassy sheen when wet, raw diamonds reflect light in a dull, almost oily way. Some call it adamantine, but that's misleading in a creek bed context where everything is wet and shiny. The real trick is to look for the lack of bright reflections. A diamond scatters light more diffusely, and if you're looking at a transparent pebble that sparkles too much, it's probably quartz or glass. This becomes even more noticeable under sunlight. While quartz pops, diamond just sits there, calm, subdued, unsettling in its confidence. Form is the next big separator. Diamonds typically form in octahedrons, 8 faces that meet in sharp or slightly rounded points. But in rivers, natural wear rounds off the edges. Even so, the base geometry often remains visible, Imagine two pyramids stacked base to base. If a pebble vaguely holds that shape, with symmetrical sloping sides and no obvious fracture lines, it's worth a closer inspection. Also watch for surface textures like trigons, tiny triangular pits or ridges etched by time and water, often unique to diamond. Then comes translucency. Unlike most quartz pebbles, which are either fully transparent or milky, a rough diamond tends to be semi-translucent with cloudy interiors or zoning lines. It might let light in, but not all the way through. Hold it up. If it scatters light internally without revealing a clear image behind it, you're in the right ballpark. It feels denser too, with a weight that doesn't quite match its size. In hand, that weight is subtle, but once you've handled enough creek stones, the difference becomes instinctive. One of the fastest screening tools here is the scratch test, but use caution. Diamond is the hardest natural substance, rating 10 on the Mohs scale, but hardness alone doesn't distinguish it, as quartz 7, sapphire 9, and moissanite 9.25 can all resist casual scratches. More telling is that a diamond will scratch every other stone, and most steel tools, without being scratched itself, carry a small piece of corundum or 6 sandpaper. Mohs 9, if your suspected stone shrugs it off without a mark and scratches the tester, it may be worth keeping. But no single visual or tactile clue is conclusive. The aim is to stack the odds. A crystal with greasy luster, an octahedral habit, cloudy translucency, and exceptional hardness deserves a place in your pouch, especially if it turns up in sediment also rich in indicator minerals. Even so, many locations yield stones that pass some but not all of these checks. That's where geology enters, because the stream doesn't lie, and some bends speak louder than others. Rivers don't just move water, they tell stories in sediment. And if you know how to read their meanders, benches, and gravel layers, they'll reveal where diamonds are most likely to have paused on their long journey from pipe to pan. Not all streams are equal. To have any chance of yielding diamonds, a creek or river must intersect the right kind of geology. Most critically, regions downstream of ancient, stable cratons where volcanic pipes once punched through the Earth's mantle. In regions like the Kopval Craton in South Africa, the Slave Craton in Canada, or the São Francisco Craton in Brazil, diamonds originated deep underground, brought to the surface by explosive eruptions of kimberlite or lamproite. Over millions of years, weathering breaks these pipes apart, releasing diamonds and their telltale companions into surrounding soils and waterways. But the process isn't random. Water follows gravity, but it also carves selectively, eroding soft matrix while concentrating dense minerals in certain predictable zones. Look first at river bends, especially tight meanders where water slows. On the inside of these curves, current velocity drops just enough to deposit heavy materials. If the surrounding geology is right, and if a volcanic source once sat upstream, this is where garnets, magnetite, and possibly diamonds settle. The gravel bars just downstream of natural constrictions, like rock outcrops or fallen trees, also trap heavies in their eddies. Old-timers called these pockets, and when sampled properly, they offer excellent first-pass locations for indicator minerals. Then consider terraces, flat, elevated former riverbeds now stranded above the modern stream. These paleochannels often hold richer concentrations than the present flow, especially if glacial or tectonic activity shifted the river over time. The older the terrace, the more concentrated the heavies may be. A test pan from such a bench, particularly where black sands accumulate near bedrock, can yield surprising clues missed by modern watercourses. Subsurface contact points matter too. Diamonds, like gold, tend to settle at the bottom of a gravel layer, ideally on impermeable bedrock or clay. As the current loses strength, denser materials drop first, diamonds included. That means the richest layers are not at the surface, but just above this hard boundary. Digging down 30 to 60 centimeters may reveal a heavier mineral concentration missed entirely by surface sampling. This depth-dependent layering is critical for identifying real potential in seemingly barren streams. Regional geology can't be ignored, even in areas with perfect sediment traps and black sand buildup. If the upstream terrain lacks ancient kimberlite or lamproite exposures, or if glaciation stripped those pipes long ago, the odds drop sharply. That's why topographic maps and historical geological surveys are as important as boots on gravel. They show whether your stream cuts through favorable terrain or merely collects superficial runoff. If the terrain checks out and the river's geometry suggests strong sediment sorting, it's time to look closer at what's actually in the pan. Because the first reliable signs of diamonds aren't the stones themselves, but what rides beside them in the heavy concentrate. Among the swirling mix of creek gravels, only a narrow suite of minerals consistently travels with diamonds. These indicator minerals are more than geological companions. They're forensic clues that narrow vast stretches of terrain into target zones. If you find the right mix, even in trace amounts, it can shift your search from speculative to strategic. And in fluvial environments, the three standouts to look for are pyrope garnet, ilmenite, and magnetite. Pyrope garnet is the front-runner. A magnesium-rich, deep purple to reddish mineral, pyrope forms under high-pressure mantle conditions, just like diamonds. When kimberlite pipes erode, pyrope is often released in far greater quantities than diamonds themselves. That's good news. Finding even a few grains of pyrope in a pan means you're potentially within transport distance of a primary diamond source. Under natural light, these garnets look like tiny, translucent red beads. In black sand concentrates, their vivid coloration stands out against darker minerals. Crushed gently between steel plates, they fracture conchoidally rather than crumbling like glass. Ilmenite is next in diagnostic value. This black, metallic-appearing mineral is titanium iron oxide with high density and moderate magnetic properties. A simple handheld magnet passed over your dry pan concentrate will often cause ilmenite grains to jump or shift. They resemble coarse, flattened black seeds, sometimes smooth, sometimes etched by chemical weathering. In diamond exploration, the specific variety of ilmenite can even suggest how close you are to source. But for field purposes, any significant ilmenite presence alongside garnet justifies further sampling. Magnetite, though more common, still holds weight, literally, with a specific gravity of around 5.2 g/cm superscript 3. It readily settles into the bottom layer of sluice or pan. Unlike ilmenite, it's strongly magnetic and responds instantly to a neodymium magnet. Magnetite's presence alone isn't diagnostic of diamonds, but in combination with garnet and ilmenite, it confirms proper sediment sorting and offers a check on current strength and deposition zones. A classic telltale is the black sand sandwich found in ideal deposition layers. A base layer of fine magnetite, above it a band of ilmenite, then scattered garnets, and, if you're lucky, a stray octahedral crystal. Even if no diamond appears, this sequence screams proximity to a kimberlite transport pathway. In northern Canada, this exact configuration led exploration teams to buried pipes beneath glacial till. In Brazil's Minas Gerais region, a similar mix in terrace gravels marks areas now under artisanal mining claims. To isolate indicators effectively, your sieving technique must match their size. Most indicator minerals fall between 0.5 to 2 millimeters. A number 20, 0.85 millimeters, and number 40, 0.425 millimeters. Mesh combo isolates this critical window. Anything finer risks loss. Anything coarser dilutes your concentrate with non-diagnostic stones. Once sieved, let the water swirl do the rest. Indicators, being heavy, move slowly to the pan's bottom, letting lighter materials flush over the edge. But beware of contamination. Stream-side breakdowns of upstream industrial materials, like furnace slag or road debris, can produce magnetic grains that mimic ilmenite or magnetite. In such cases, texture and luster become key. Real indicator minerals are naturally smoothed but not glassy. Their luster is often metallic but subdued. If a black grain feels oddly sharp or angular, it's more likely man-made. When indicator minerals show up, especially more than one type in a single pan, it's no longer just a hunch. It becomes a signal worth tracking upstream or gridding systematically. But to make that decision with confidence, you need a field test that shows whether these indicators are just passing through or pointing to something just beneath the surface. A single pan can tell you more than a full day of surface scouting if you know what constitutes a hit. Most hobbyists stop short when they find a shiny pebble or two. But in serious diamond prospecting, the absence of diamond isn't the same as absence of potential. Instead, it's the ratio and concentration of indicator minerals in a small sample that gives the green light for deeper work. The first pan test isn't about finding the diamond. It's about justifying the hunt. Start by choosing the right spot. An inside bend with visibly sorted gravels, or a midstream bar where heavy black sand builds up. Using a shovel, remove a controlled volume of sediment, roughly 10 to 15 liters, from a consistent depth, ideally down to the first clay or bedrock contact. This base layer is where heavier materials like garnets and any possible diamonds will concentrate. Avoid scooping random surface gravels or silty overburden. It dilutes the test and masks real signals. After sieving with a number 20 mesh to eliminate coarse clasts, pan slowly with attention to how the sediment separates. Watch how the lighter sands and micas flush away. What remains, usually a small wedge of dark concentrate, is where the Real reading begins. If the pan shows 2 to 4 visible garnets in that final inch, that's a moderate but promising result. Add to that a few flat black grains that shift subtly under a magnet, and you've got ilmenite, possibly from a weathered kimberlite. A single pan with this trio, garnet, ilmenite, magnetite, immediately justifies a larger sampling grid. The concentration matters. 1 garnet per pan is not dismissible if it shows up consistently across different points in the same bend or bar. But a sudden spike, 5 garnets in one pan, then none in adjacent samples, suggests a narrow transport path or a residual pocket. Field geologists often use a rough metric. 10 indicator minerals in 10 liters of sediment equals a strong anomaly, especially if the garnets show deep purple or red coloration, implying mantle derivation. Color and luster under magnification also tell more than quantity alone. High chromium pyrope garnets, for example, appear richer and often contain telltale inclusions visible under a hand lens or loupe. These inclusions, tiny metallic flecks or needle-like structures, hint at ultramafic source rock and significantly raise the signal-to-noise ratio of your find. Also worth noting, in river systems that have undergone multiple sedimentation cycles, older terraces may show higher indicator concentration than active channels. If your first test pan from a terrace gravel yields richer heavies than the modern creek, that suggests ancient alluvial retention. Exactly the kind of environment where diamonds quietly accumulated over time. But here's the crucial point. A good first pan doesn't need a diamond. It needs a pattern, one that can be replicated, expanded into a grid, and validated by repeatable sampling. Only then can you begin to separate geological coincidence from a real pipeline of erosion and deposition. And yet, just when a site looks promising, the next test may raise a troubling question. What if the clear, angular crystal you just found isn't a diamond at all? It gleams just right, sits heavy in the pan, edges sharp but worn, like something that's traveled. For a moment, it seems certain you found a raw diamond. But a closer look under the loupe, and doubt creeps in. Double refraction. Slight too much clarity. Or worse, it's too light in the hand. What you've likely found is zircon, quartz, or even a shard of man-made glass, each deceptively convincing in the field. False positives plague diamond hunting. Zircon, especially, is notorious for impersonating raw diamonds. It forms as tetragonal crystals, often highly transparent and unusually dense, with a specific gravity close to 4.6, heavier than diamond. This density can fool experienced hands. But zircon reveals itself under polarized light. Its double refraction splits the image of a gridline or facet edge viewed through the stone. Diamond, being singly refractive, keeps lines crisp and undoubled under magnification. Then there's quartz, far more common than any real indicator and endlessly deceptive. Creek-worn quartz can take on rounded forms and may appear nearly colorless. But its lower specific gravity, around 2.65 g/cm superscript 3, makes it feel light compared to diamond. It also shows a brighter, glassy luster that catches too much light. A scratch test may eliminate quartz. Diamond will scratch it effortlessly. But caution is required not to damage a true find in the process. Use a known quartz point as a disposable test object. If your stone slices into it cleanly, diamond remains in play. Moissanite presents the most technologically tricky deception. A lab-created silicon carbide, it closely mimics diamond's hardness, Mohs 9.25, luster, and general appearance. It's also often cut as a faux gem, and occasionally ends up in sediment due to jewelry loss or waste. But moissanite's tell comes from two main factors: double refraction and electrical conductivity. Viewed under 10 times magnification, moissanite often shows a doubled facet edge, unlike a true diamond. And when tested with a basic electrical conductivity meter, moissanite typically conducts. Diamond does not. Even high-index glass can occasionally fool the unprepared. Some industrial glasses used in optical or ceramic applications have refractive indices approaching that of diamond. Worn fragments may be dense, rounded, and misleadingly lustrous. But their uniformity gives them away. No internal zoning, no natural inclusions, and a slightly dead look when rotated under light. In UV light, they rarely fluoresce, while natural diamonds often emit a soft blue glow, though not consistently enough to rely on fluorescence alone. One simple field trick, particularly against quartz and glass, is weight-to-size intuition. After handling enough river gravels, you'll develop an instinct for how heavy a 5 mm pebble should feel. If one feels distinctly off, denser than it looks, it warrants further testing. This intuitive density check, paired with surface texture, diamonds show distinctive etching or trigons, help sort the first tier of finds. But in the end, it's not the stone that tells the truth. It's the test. Each false positive adds to your calibration. Each mistake teaches your eye what to discard faster next time. Because the margin between illusion and value in this field is thin. And when you finally isolate a candidate that passes these early screens, it's time to bring out more definitive tools. Ones that confirm or disprove with thermal precision. The difference between speculation and confirmation often comes down to heat and current. In the field, thermal conductivity testing has become the most decisive tool for separating rough diamonds from their many imitators. While most materials in your pan may pass visual checks or even feel right in hand, a simple 5-second test with the right tool can settle the question without waiting for a lab. Diamonds conduct heat faster than nearly any other naturally occurring substance. More than copper, more than silver. This property is stable and diagnostic. Handheld thermal testers, originally developed for gem dealers, now fit easily into a field kit. These pen-style devices use a metal tip to apply a small amount of heat to the surface of the stone. If the device registers an immediate spike, it's reading diamond-grade thermal flow. Quartz, zircon, and glass barely respond. Before testing, the stone must be clean and dry. Water or mud can interfere with readings. Touch the tip firmly to the flat surface of the stone, not an edge. A genuine diamond will cause the device to beep or register on the high end of the scale. Moissanite, however, complicates things. It also conducts heat well enough to trick basic thermal testers, which is why most field kits now include combination units that test both thermal and electrical conductivity. This is where the real line gets drawn. Moissanite, unlike diamond, conducts electricity. A 2-in-1 tester applies a mild current to the stone after the thermal test. If the device detects electrical conductivity, the sample is moissanite or another synthetic conductor. If it passes thermal and resists electrical flow, it's likely a natural diamond, or at least not moissanite. Field protocols matter here. Never test when ambient temperatures are extreme, below 5 degrees Celsius or above 35 degrees Celsius, as it may affect both the probe and stone surface. Let the sample and tester equilibrate to the environment for a few minutes before use. And always test more than one surface of a candidate stone, especially if it's rough or uneven. A single failed contact doesn't rule a stone out. Keep in mind, these testers work best with stones above 2 millimeters in size. Very small crystals may yield ambiguous readings due to insufficient contact surface. For these, specific gravity testing or controlled light analysis becomes more useful. But in the 3 to 10 millimeters range, where most field-discovered roughs fall, thermal/electrical combination testers offer a powerful, portable filter. Even so, a correct thermal signature doesn't equal high value. Industrial-grade diamonds, cloudy, fractured, or off-color, still register like high-quality gems. This tool sorts authenticity, not market grade. But that's precisely what makes it essential in the field. It tells you when to escalate, when to document the GPS, when to grid for more samples. Because once you've confirmed a thermally conductive, non-electrically conductive stone in the pan, especially in the company of garnet and ilmenite, it's time to scale up. The individual pan test has served its purpose. Now the question becomes, how do you process more sediment faster, without missing the prize? Speed without loss. That's the core challenge of moving from test pans to bulk sampling. If a single pan has yielded a strong mix of indicator minerals or a suspected diamond, you're now looking to isolate more material from the same horizon while preserving fine detail. That's where sieving smart makes all the difference. It's not just about volume. It's about trapping the right size fraction, efficiently separating float from density, and keeping those tiny, high-value fragments from slipping through. Most field-grade diamond indicators, and diamonds themselves, fall within the 0.5 millimeters to 3 millimeters range. Anything larger is rare. Anything smaller becomes increasingly difficult to detect or test in the field. To isolate this critical window, you'll need a nested sieve stack, typically a number 20, 0.85 millimeters opening, on top of a number 40, 0.425 millimeters. Material retained on the number 20 screen includes coarser garnets, ilmenite fragments, and larger rough stones. The finer screen captures the denser, more subtle indicators often missed by eye alone. Begin by shoveling sediment from the exact layer that yielded your original positive pan, ideally 30 to 60 centimeters deep, or down to bedrock or clay. Soak the sediment in a large bucket or basin before sieving. This breaks surface tension and liberates clay-bound fines. Pour water gently through the sieve stack, agitating by hand. Avoid aggressive shaking. It can force denser particles through before they've had a chance to separate by size. Once sieved, spread each size fraction separately on a white or black inspection tray. The color contrast makes garnets pop and helps spot opaque grains. With a neodymium magnet, sweep across the tray to pull any magnetic materials aside. This separates magnetite and some ilmenite quickly. What remains, especially if it shows color or luster differences, deserves close inspection under loupe or field scope. The number 20 fraction is where most recognizable stones land. Here, you may find coarse ilmenite, visibly zoned garnets, and occasionally a candidate diamond. These stones tend to resist movement in water. They cling low in the pan or stick to the bottom of a sluice. The number 40 layer, though more tedious, often carries finer ilmenite dust or small pyrope grains. Dismissing this size range risks losing the very indicators that guided exploration in historic finds, particularly in worn-down cratonic terrains. For extended sampling, dry sieving can be used once the material is pre-cleaned and moisture-free, but wet sieving preserves the natural behavior of the minerals under riverine conditions. It mimics what a pan or sluice would naturally do: layer and isolate by density and hydrodynamic drag. What you're simulating is the river's own sorting mechanism, accelerated. But here's the catch. You might go through a dozen sieved buckets with no new hits after your first promising find. Does that mean the signal was a fluke? Not necessarily. It might signal a very narrow channel or pocket. Or it might point to a false trail entirely. That possibility brings us to a critical checkpoint in any diamond hunt. When your indicators surge but no diamonds appear. Because sometimes you find all the right clues, but not the prize. And understanding why can save months of wasted effort or point you to something even bigger, just upstream. It's a moment that tests every prospector's resolve. You've logged consistent garnet and ilmenite counts across multiple sample points, confirmed magnetic response, sieved clean fractions, even found a few promising stones. But pan after pan, the diamond remains absent. It feels like a contradiction, the classic field paradox of everything but the stone. The explanation often lies not in the gravel, but in the hidden journey upstream. Because in diamond-bearing environments, indicator abundance without diamonds is not failure. It's a signpost with conditions. One of the most common causes is glacial transport. In regions once covered by ice sheets, Canada, Northern Europe, parts of the northern United States, glaciers scraped kimberlite pipes and carried the debris hundreds of kilometers. As they melted, the indicators dropped out first due to density, leaving behind garnet and ilmenite-rich till far from any diamond source. That's why some modern creeks show a strong indicator signature in sediment that's not geologically connected to any known pipe. You're reading a glacial echo, not a current-day deposition. Alternatively, you may be downstream of a worked-out source. Some diamondiferous pipes shed their load millions of years ago, feeding ancient rivers and alluvial systems that are now buried or eroded. Modern streams may still carry traces of those indicators, garnet, ilmenite, but the diamonds have long since been carried beyond reach or trapped in paleochannels inaccessible without excavation. In Brazil's Jequitinhonha Valley, for example, extensive indicator trails can lead to gravel with no remaining gem-grade content. All the value is in deeper layers mined decades ago. There's also chemical sorting to consider. While garnets and ilmenite are robust and chemically stable in most conditions, diamonds are not impervious to surface weathering. They can be abraded, fractured, or even dissolved in certain soil chemistries over geological timescales. In iron-rich or acidic conditions, such as boggy floodplains or lateritic terrains, diamonds may degrade while indicators persist, especially if exposure cycles were prolonged. But perhaps the most insidious reason for diamond absence in indicator-rich zones is dilution. In braided rivers or wide channels with high sediment loads, even if diamonds exist, they may be so dispersed that your sampling grid misses them entirely. If you're pulling 10 garnets per 10 liters in every pan, but never turning up a stone, the diamond count may simply be too low. 1 stone per cubic meter or less. That doesn't mean it's not there. It means the deposit is uneconomical, or deeply buried under newer sediment. To diagnose this, plot your sample points on a topographic map. If indicator counts show a decreasing trend downstream or tighten around a tributary junction, you may have overshot the target. Conversely, if concentrations are flat across wide terrain, your sample grid may be too coarse to detect a narrow diamond train. In these cases, reduce your sample spacing to 5 meters or less along likely deposition zones, inside bends, plunge pools, gravel traps. And yet, this frustration has a hidden upside. An indicator-rich site with no surface diamonds can be far more valuable in the long term than a single stone anomaly. It tells you the system works, that the river sorts, the geology cooperates, and the markers behave predictably. With that framework, you're ready to transition from chance to methodology, guided not just by luck, but by protocols that professional geologists use to decide where to dig, how deep, and what to test next. When raw instinct hits a wall, professionals fall back on structure. That's why, in field exploration, especially for diamonds, nothing replaces a proper grid and documentation protocol. What might look like a lucky find to an amateur is, to a geologist, a data point. One in a series that forms a pattern, validates a source, or rules one out. And when it comes to maximizing recovery and reducing waste, the gold standard is a tightly managed grid sampling operation. The core principle is repeatability. A single promising pan means little unless it can be replicated in adjacent test points. That's why geologists lay out grids, often 5 by 5 or 10 by 10 meters, across high potential zones. Each square is a controlled test area, sampled at the same depth and processed using identical sieving and panning techniques. Sample bags are numbered, coordinates logged by GPS, and detailed field notes taken on concentration, grain type, and any unusual findings. Let's say your initial pan turned up garnet and ilmenite near a creek bend. Rather than wander upstream hoping for more, the structured approach is to plot 10 sample points at regular intervals along that inside bend, extending into adjacent bars and terraces. Each is dug to consistent depth, ideally down to the heaviest concentration layer just above bedrock or dense clay. At each point, take a fixed volume of sediment, say 10 liters, and record it as sample A1, A2, A3, and so on. When these samples are processed and the number of indicators per pan are tallied, you build a heat map of mineral concentration. This map tells you more than any single find could. If indicator counts increase toward a particular direction, that vector points to the likely source or richer pocket. If they suddenly drop off, you may have crossed out of the plume or hit a barrier, perhaps a sediment trap or a change in current velocity. Even null results matter. A well-sampled grid with 3 high-count nodes and multiple blanks helps define the boundaries of a productive lobe. This spatial control is what separates geological investigation from speculation. Beyond mapping, these protocols help preserve evidence integrity. It's not uncommon for labs, investors, or even regulators to ask for provenance. A random stone found without context raises questions. A stone retrieved from sample before, documented on a grid map with repeatable results and accompanying indicator counts, has scientific and legal credibility. For those seeking permits, partnerships, or claims, this kind of record-keeping becomes non-negotiable. Field photos also matter. For each grid point, take a photo of the site before and after sampling, showing tools, depth markers, and sample bags. Not only does this support documentation, it also helps later if terrain changes, floods, landslides, or human activity can obscure your previous work. With photos and GPS logs, you can reoccupy points, retest, and build a time series model of sediment behavior across seasons. It's worth noting that most commercial diamond discoveries didn't begin with a single stone. They began with indicator anomalies mapped through this process. In the Canadian North, Grids hundreds of meters wide were laid to track ilmenite counts to their apex. In Angola, grid sampling along dry riverbeds revealed buried terraces unseen from satellite imagery. The discipline pays. So if your indicators are saying yes, but your diamonds haven't appeared yet, the path forward isn't a new river. It's a clipboard, a sieve, and a grid. Because only through systematic sampling can you decode whether you're skimming leftovers or standing over the mouth of a hidden pipe. Not every beautiful bend or gravel bar holds promise, no matter how rich it looks on the surface. The harsh truth is that diamonds don't occur evenly across the globe. They cluster, geologically bound to the bones of ancient continents. That's why understanding where the hunt doesn't work is just as critical as knowing where it does. If you're not standing on stable Archean craton or downstream from one, your chances of finding a diamond, no matter how disciplined your grid or how perfect your pan, drop to near zero. Cratons are the cores of continents, ancient, thick, and tectonically stable pieces of lithosphere that haven't significantly moved for billions of years. It is under these ancient blocks that the mantle conditions necessary for diamond formation once existed. High pressure, high temperature, and deep carbon-rich fluids. When kimberlite or lamproite pipes punched through to the surface, they pulled diamonds up through these zones. That's why virtually all economically significant diamond deposits occur on or near cratons. In southern Africa, for instance, the Kopval Craton underpins all major diamond fields, from the famous Kimberley pipes to alluvial deposits downstream in Botswana and Namibia. In northern Canada, the Slave Craton supports fields near Lac de Gras and Snap Lake. Russia's Yakutia diamonds trace back to the Siberian Craton. In Brazil, the São Francisco and Amazonian Cratons define the range of viable diamond zones. These are the names that matter. Not just river names, but the ancient terrains beneath them. Outside of cratonic zones, kimberlite-like rocks may still exist, but they rarely carry diamonds. Volcanics from more mobile belts, such as those found in younger orogenic regions like the Andes or the Himalayas, simply don't originate from the necessary depth or pressure regime. Even within cratons, not every pipe is diamondiferous. That's why prospecting focuses so heavily on indicator mineral chemistry, not just presence. This geographical limitation means that creeks and regions like much of the eastern United States, Western Europe, or Southeast Asia offer poor odds for diamond discovery. The lack of ancient cratonic support means no mantle-derived kimberlite, no deep-source diamonds. You might still find quartz, zircon, even garnet, but they lack the genetic link to diamondiferous systems. The geology doesn't lie. Satellite imagery and global geological maps, many now publicly accessible, can help filter search areas before a single shovel hits gravel. Tools like the USGS Global Crustal Map or Canada's GSC bedrock layers show which terrains qualify. If the creek you're sampling doesn't cut through sediment derived from cratonic rocks, or doesn't sit downstream of known kimberlite fields, it's best considered a training ground, not a viable target. Even within favorable regions, scale matters. Some alluvial fields extend for kilometers. Others are no more than 100 meters across. Microterraces, perched on ancient floodplains or buried under newer sediment, can hold more value than entire modern streams. So terrain alone isn't enough. The local geomorphology must cooperate, offering traps where diamonds could logically have accumulated and persisted. This geographic filtering doesn't just protect your time. It protects your energy and resources. It narrows thousands of square kilometers down to the few hundred that might yield results. And if your field area checks out on this cratonic litmus test, it's time to scale up your process. Because even the right ground won't give up diamonds easily unless your recovery system is efficient enough to catch them. When a pan starts to yield promise, but the volume limits your pace, it's time to graduate to equipment that mimics nature, at scale. That's where sluices and jigs come into play. These aren't just tools for gold miners. Adapted correctly, they're highly effective for concentrating heavy minerals and potential diamonds from bulk sediment, especially in creek environments with accessible water flow. But efficiency here isn't about size. It's about sensitivity to density, turbulence, and particle shape. A sluice works by exploiting gravity and flow dynamics. Water is directed down a gentle incline through a channel lined with riffles, raised bars or matting that interrupt the flow. Lighter particles stay near the surface and are flushed out. Heavier ones, ilmenite, garnet, and potentially diamonds, settle into the riffles and stay behind. But standard gold sluices are tuned for flakes and nuggets, not the small, dense pebbles that diamond-bearing gravels contain. That means modifications are necessary. First, adjust the angle. A 5 to 8 degree slope allows heavier materials to settle while maintaining flow. Too steep, and you lose fine heavies. Too flat, and the sluice clogs with light sediment. Second, use a sluice mat or miner's moss beneath the riffles to catch microparticles. For diamonds, riffles spaced more closely than gold sluicing, typically 1 to 1.5 centimeters apart, retain more of the smaller, rounded heavies like garnet and dense stones between 0.5 and 2 millimeters. Another refinement is flow rate. Use a controlled feed, pouring sieve sediment in small batches rather than dumping full buckets at once. This gives the system time to stratify materials and allows you to monitor which fractions are being retained or lost. Periodically check tailings to ensure garnets or dark heavies aren't being washed out prematurely. If they are, reduce water flow or adjust slope until retention improves. For those with access to portable gear, a small jig can outperform a sluice in certain creek settings. Jigs operate by pulsing water through a bed of gravel, forcing materials to stratify by density in vertical motion rather than horizontal flow. In this oscillating environment, diamonds, denser than most surrounding minerals, drop quickly to the bottom of the jig cell. Well-calibrated jigs can process large volumes in short time with remarkable retention, especially when tailored for particles under 10 millimeters. But both methods require clean, pre-sieved feedstock. Large organics, silt, and floating debris reduce effectiveness and increase loss. Always run material through a #10, #20 screen before feeding your sluice or jig. The goal is to control variables, particle size, water flow, and sediment load, to isolate the densest, most promising fragments without relying on luck. Recovery runs should be time-limited. After 2 to 3 hours of processing, stop and clean the sluice or jig. The concentrate, often less than 500 grams, holds your potential diamonds along with garnet, ilmenite, magnetite, and whatever else the system has trapped. Pan this slowly, under full light. Use a magnet to clear obvious magnetite. Then loop each non-magnetic grain larger than 0.5 millimeters. You're looking for anything octahedral, translucent, or unusually heavy. These bulk systems bridge the gap between exploratory and productive. They allow for meaningful sediment throughput, giving you the volume needed to encounter low-frequency targets like diamonds without the fatigue of hundreds of manual pans. They also help identify productive zones by tracking yield per bucket, refining your grid into richer zones. And yet, even after all that, many of the stones that pass through your sluice and into your pan will still leave you guessing. Some will glow, others will stay dark. Some will seem too perfect to be real. That's when it's time to bring in light, quite literally, and let ultraviolet and optical tests begin narrowing the field. It sits in the pan, angular, colorless, and just heavy enough to raise an eyebrow. You've sieved it, sluiced it, isolated it. But is it a diamond? You could send it to a lab, but that takes time and money. Instead, the next round of in-field filtering brings optics into play. ultraviolet fluorescence and loupe-based visual inspection. Neither method is definitive on its own, but together, they sharpen the lens through which potential diamonds are judged. Start with UV. Many natural diamonds fluoresce under short-wave ultraviolet light, typically emitting a soft blue glow due to trace nitrogen impurities. This effect isn't universal. Only about 30 to 40% of diamonds fluoresce, and even fewer do so strongly enough to be seen in broad daylight. But when present, it offers a quick, portable confirmation step. With a battery-powered shortwave UV lamp, position your candidate stone on a dark, matte surface. Felt or black sandpaper works well. In darkness or a shaded environment, turn on the lamp. A true fluorescence will appear as a uniform, bluish glow, sometimes with hints of green or yellow depending on the stone's chemistry. Quartz, glass, and zircon rarely fluoresce this way. Quartz may glow under long-wave UV, but the tone is more of a faint white or violet. Moissanite, when fluorescent, often emits a greenish tint, setting it apart. A strong fluorescence isn't proof, but in conjunction with other positive tests, it becomes a meaningful data point. Next, shift to the 10 times loupe. Under magnification, the surface of a diamond often reveals characteristic etching. Microscopic trigons or triangular pits form during natural growth or erosion. These are rarely found in quartz or glass, and appear in patterns unique to diamond crystal habit. Rotate the stone slowly under direct light. Trigons typically cluster near facet intersections or along edges and may be easier to spot if the surface is slightly frosted. Look for doubling. Moissanite, one of diamond's closest imposters, exhibits double refraction. When viewed at an angle under the loupe, facet edges or internal inclusions appear to split into two parallel lines. Diamonds, by contrast, are singly refractive. Clean, sharply defined edges under magnification favor a positive ID. If you're unsure, draw a grid line on white paper and place the stone over it. A true diamond will transmit the line with little distortion. A doubly refractive stone will blur or split it. Also note luster under the loupe. Diamond surfaces reflect light with a subdued but intense brightness, neither too glassy nor metallic. Stones that shine too brightly or reflect harshly often turn out to be high-index glass or zircon. Glass also lacks internal structure. Under magnification, it appears overly smooth, with trapped gas bubbles or swirl lines. Natural diamonds often contain minute inclusions, tiny dark dots, cloud-like wisps or feather cracks, rarely found in man-made materials. If your stone passes thermal and conductivity tests, shows trigons or single refraction under magnification, and exhibits fluorescence, the odds tilt sharply toward a real diamond. But one key metric still remains out of reach in the field: density. And that test, as rudimentary as it seems, often delivers the final word. Specific gravity is often the quiet proof that other field tests can't simulate. While thermal conductivity and optical inspections help narrow down possibilities, the density of a stone offers one of the most decisive non-destructive tests available outside a lab. Diamond has a well-established specific gravity of about 3.52 g/cm superscript 3, placing it above quartz, 2.65, glass, approximately 2.4 to 2.8, and even most garnets, 3.1 to 3.4. So when you're holding a specimen that checks every other box, luster, habit, non-conductivity, a simple water test might be the final confirmation. To perform it in the field, you only need a small digital scale accurate to 0.01 grams, a fine thread or monofilament line, a container of water, and a steady setup to suspend the stone without letting it touch the sides or bottom. Begin by weighing the stone dry. This is your baseline mass. Next, suspend it in water using the thread and record its underwater weight. The difference between the dry and wet measurements reveals the volume of water displaced, which is directly tied to the stone's density. The math is straightforward. Divide the dry weight by the difference between dry and submerged weight. For example, if the stone weighs 1.00 g dry and 0.72 g in water, then its specific gravity is 1.00 divided by 1.00 to 0.72, which equals approximately 3.57, a result that strongly supports a diamond identification. Readings closer to 2.6 suggest quartz. Values over 4.5 may indicate zircon or other high-density lookalikes. Field accuracy depends on a calm environment. No wind, stable scale, no air bubbles clinging to the stone, and a completely submerged setup without contact. Repeat the test twice for consistency, discarding outliers. This method is especially valuable for small stones in the 2 to 5 millimeters range, precisely where many natural diamonds occur in alluvial settings. Even if the reading aligns with diamond density, it doesn't speak to clarity, color, or market grade, but it does justify the next step: verification through professional analysis. Because once a stone passes thermal, conductivity, optical, and gravity tests in sequence, it graduates from maybe to probable. And when 3 samples in a single stream pass all 4 checkpoints, it's no longer a matter of chance. It's a discovery zone. Sending a specimen to a lab isn't about hope. It's about calculated escalation. Field testing gets you close, but laboratory analysis provides the definitive answer: crystal structure, impurity profile, and certified origin if needed. The real challenge isn't finding something interesting. It's knowing when that interest crosses the threshold into value. Labs don't work for free, and turnaround times can stretch into weeks. That's why experienced prospectors follow a simple rule: send it only when field evidence reaches critical mass. That threshold usually starts with consistency. One stone with a high specific gravity and thermal signature is interesting. 2 stones from the same grid zone, both showing positive results across thermal, conductivity, luster, and gravity tests. That's a pattern. 3 or more. Now you're tracking a vein, not a fluke. Once multiple samples from different pans or grid points return similar results, the probability that you're sitting on a real diamond-bearing deposit increases exponentially. That's when lab confirmation becomes worth both the cost and the time.